So today we're happy to have them on. We're going to talk about exotic theory and condensed matter physics. Please, so.
I don't see it's better if I sit down or
it's up to you.
Yeah.
You want to walk around or your first item of the question is duration.
okay, so let me first thank the organizers for giving me this opportunity to give a talk. I'm going to tell you something that I've been thinking about with my student Ishian Lu, and we haven't finished this project yet. So a lot of things that you will hear are pretty incomplete, but I think the direction that we are going might be interesting. Okay, so the plan of my talk is to first introduce the setup, which is a rotating superfluid. When you have a superfluid, here I'm going to do mostly two-dimensional superfluid. Let me try to see if I can write here. 2D superfluid. Okay. So we are going to consider two-dimensional superfluid that is rotating. When a superfluid rotates, we have a vortex lattice, and the oscillation of that lattice is called the Kachenko mode that we are going to try to understand. And this Kachenko mode we mentioned has an exotic dispersion relation, and the effective field theory that described that Kachenko mode is turned out to be also quite exotic in a sense that I'm going to tell you about. And we first will consider the linear regime quadratic of the quadratic Lagrangian of this theory, and then go to nonlinear regimes and talked about the role of area preserving leak as the an interesting symmetry of this theory. So here is the picture of rotating superfluid. When you have a superfluid that rotates, the way that it accommodates rotation is by creating little vortices. These vortices, each of these vortex carries a unit circulation. That is, if we take the integral of the velocity of this of the flow of the superfluid flow around one of the vortex, we see a quantity that is quantized, that is equal to, so here the formula here is derived by noting that the superfluid velocity is h bar divided by m times the gradient of the superfluid phase. If you integrate the superfluid, the gradient of the superfluid phase around a vortex, you get 2 pi. Elementary vortex would have delta, the jump of this phi into 2 pi. And so you get a quantized circulation, 2 pi over 2 pi h bar over m. And that means that the number of vortices that one creates is completely fixed by the how fast one how fast the boundary of that superfluid moves. So this picture is from an experiment by Ketterle in 2003. That was one of the evidence that in ultra cold atoms, ultra cold atomic gas that they have created in the laboratory, the ground state is actually a superfluid. That is a very convincing evidence. And this is probably the only system one can image the superfluid vortex in such a visual way. In helium-4, if one rotates helium-4, in principle there could be vortices. There should be vortices, but to see these vortices is much more difficult. If there is any question during my talk, please interrupt me at any time. Yeah, maybe judging by the number of slides that I have, I will finish quite early. And so if there is no question, then we're going to waste time. I'm going to waste my a lot of time that I was given. And so Okay, the Kachenko mode is the elastic wave that propagates on this lattice of vortices. So this lattice of vortex is very similar to a crystal in solid state. And so when we make these vortices, the position of each of the vortex, we allow it to fluctuate, then we should expect some kind of a sound wave that propagates. And that problem thing was considered by the Soviet physicist Kachenko around 1965 and 1969. I could not find anything about him or about his life, except there is a review by Sony in 2013 that mentions that he wrote very few papers, but all of them are very high quality. So this elastic wave propagating on the vortex lattice was also seen in 2003 in the, I'm not sure about the date, in the BEC of cold atoms, and they've seen this wave almost visually. That is, you make a snapshot of the vortex lattice, and you see a pattern of deformation that's consistent with having a Kachenko mode propagating on it. And a long time ago, it was speculated that the Kachenko mode is also related to an oscillation mode of a pulsar, the Crab pulsar. One idea of the core of a neutron star is that it is a superfluid. And when a superfluid rotates, there is vortex lattice. And that the existence of its vortex lattice explains several things. But it's a couple of things in the physics of neutron star, and one of these may be related to the mode of the propagation of the Kachenko mode. Okay, so yeah.
Is there a reason why a vortex lattice of unit circulation vortices is preferred over, say, like just one big vortex of like large circulation?
It's because the energy. So the question is why the lattice of elementary vortices is favorable compared to one big vortex with n quantum number n. And the reason is that the energy of a vortex is proportional to v squared, and v grows like n. So if you have one big vortex, then the energy is going to be n squared, and that.
And would there be a regime where, like, if the number of vortices would be too large, the Coulomb repulsion between them might cause the latter to be more favorable?
So here, roughly speaking, you put your finger on the right picture. Each of these vortex can be thought of, as we mentioned, as a charged particle, and they interact with each other through a Coulomb interaction. So two of these particles, if you try to push them together, you will have to overcome a lot of potential energy. So that's why all these, if you put n of these vortices in one place, the more energetically favorable configuration is to have them spread out. Yeah. And so one can also, but what I've seen in this picture also can show numerically that the triangular lattice is most favorable from the energetic point of view. The Kachenko mode, though it's elastic wave like a sound wave in a solid, has a quadratic dispersion, omega equal k squared at small k. It's a known fact. I think it wasn't that quadratic dispersion didn't appear in the first papers by Kachenko, but when the calculation is generalized to compressible fluid, then people see that this omega, the dispersion has to be quadratic. And that then there is two questions that appear. What is the reason for this quadratic dispersion relation? Why, say, if we think about the way we would derive the linear dispersion relation in the case of phonon. One way is to write down the most general effective field theory of the displacement of the lattice. And you see that there is a quadratic term in time derivative and a quadratic term in the spatial derivative. And naturally, we see that the phonon propagates with a constant speed, or it has linear dispersion relation. So what is it?
Can I ask another question? So at every momentum k, how many modes are there?
It's just one.
Just one. But actually, so if this is like the phonon, then for phonon at every, well, I mean, there are like three well, in 3 dimensions there are 3 polarizations of the phonons, and in 2 dimensions there should be 2 polarizations of the phonons. So here you say only one, or?
Yeah, we will see that this is only the only modes that propagate is the transverse phonon. The transverse, the longitudinal mode disappear, is get out, as we will see later.
Okay.
Yeah.
Okay, cool.
Yeah. So there is only one mode. Yeah.
So does this mode knows about direction of rotation?
Does the mode knows about the direction
of rotation?
Of the rotation?
Yeah, of the superfluid.
Knows in which sense? It
can something depend linearly on omega?
The dispersion relation has no information about the direction of rotation at all. But I was thinking, what is the eigenmode? I think the eigenmode to leading order in K also doesn't know about the direction of rotation at all. It might be strange, but yeah, but it's if there is information there, it's not
I would expect
obvious.
the very correction to feel it, but you have only one mode, so there probably can be no very correction.
If there is one mode, then what?
I think there is no very correction with one mode.
There's no very curvature for one mode. It's just one mode, and it's not, as we will see, its appearance is not, doesn't seem to be related to any Berry curvature. It's the other. There is another mechanism that underlies this quadratic behavior. And then there's another question that have not been addressed, at least very extensively in the literature, is what is the behavior of the decay width of this Kachenko quantum? Suppose I have I excite one single quantum of the Kachenko mode with omega equals k squared. What is the probability that it decay into 2? And that question has to be answered. The answer to this question demands our understanding of symmetries. A better understanding of symmetry of this mode would help us answer the last question. Okay, so let's first remind ourselves about the dual description of a superfluid, which in 2+1 dimension put the Namu-Goldstone boson of a superfluid to correspondence with the gauge photon, a U1 photon. The correspondence is the following: that the current, the conserved current, U1 conserved current J mu in the dual description becomes the electromagnetic field that's conserved by the Bianchi identity. So now, if I have a non-relativistic superfluid, then the Lagrangian consists of 2 parts: the kinetic energy, which is basically mv squared, but when we write it in terms of current and density, J squared divided by n times the mass, and then this term in the dual language should be E squared over B, right? And B is the magnetic field. So this formula that we have here tell us that the density is equal to the magnetic field divided by 2 pi, the number of magnetic flux quanta. So the first term might seem scary because it's non-local in the electromagnetic field, but we have to remember that the superfluid state appears only at finite density. And so when we write down this Lagrangian, what we mean is that we are working around a certain background magnetic field, B equal B0, determined by the density of the particle. And so this Lagrangian has to be expanded around this background. And then when we expand, it becomes a very well-defined linear quadratic plus cubic plus etc. term in the Lagrangian, and we get at the end, when we expand, we get something like E squared minus B squared type of Lagrangian. So the B squared term comes from the energy epsilon of n, the energy of the superfluid as a function of the density. And this is the only microscopic input that we have to put into this theory. We need to know the equation of state, that is how energy depends on the density, and then we be able to get all the information about the Goldstone boson dispersion, also about its interaction. To this order, if we go to cubic order, we also obtain the leading order contribution to the interaction between the photon. So basically, this is one of the way one can understand superfluid. It's just a Maxwell gauge field. So now we can list the differences between the Kachenko mode propagating on the superfluid vortex lattice and the usual sound wave propagating in a solid. In the dual picture, we have a vortex lattice, which is a lattice of charged particle. In the dual picture, each of the vortex become a charge of the dual gauge field. Okay, carrying a charge 1 or -1, depending on whether it's vortex or anti-vortex, and that charge is coupled to an external gauge field. And now we have this lattice, and then each of the lattice points have two things that distinguishes it from the usual like atoms in a solid. So first of all, this particle moves in a non-zero background magnetic field. While in this, that means that there is phenomenon of Magnus force. When you have the motion of a particle in a certain direction is caused by a force acting in the perpendicular direction. So this magnetic field from the previous transparency is just the density of the superfluid. So this is one difference. The second difference is that these particles interact with each other with the U1 gauge field, the photon. The U1 gauge field is not confined, not fixed. And so its gauge field has infrared behavior. And we will see that the second feature is actually the one that causes the quadratic dispersion relation. So in this language, the Kachenko mode is the result of hybridization between the phonon of the lattice and the photon that come from the superfluid. It's like a polariton in solid state physics. Okay, so let's go through the linear theory of the Kachenko mode. So in the linear theory, each of the lattice is displaced by a certain amount. That displacement, we call that U. So we have a lattice, and then a perfect lattice would be like this, and then each of these points would be displaced by an amount equal to U. And that U is a field that we assume to be smooth, varies over length scale much larger than the lattice spacing. Now, there is also a U1 gauge field. Each of these point particle is a charge under a U1 gauge field, A mu. Each of these charges move in a background magnetic field. And so that causes a Berry phase term in the Lagrangian that have the form of U cross U dot.
So does this mean that in the original picture, the translation apparatus don't commute with each other?
The translational operator do not commute, but it's commute to the
omega, right?
they commute to the total number of particles.
So Watanabe said that when you have non-commutative, when your progress symmetry has no commute, then we have only one Goldstone mode, and this Goldstone mode will have quadratic dispersion.
That may be related. So,
I think that's exactly what happens here.
Can you repeat what he's asking?
okay, so this one statement, the statement is that when you have two broken generators that commute, the commutator of these two broken generator is another generator with expectation value that is non-zero. Then instead of two Goldstone modes, we'll have one Goldstone mode.
And it will have quadratic dispersion.
With a quadratic dispersion.
Yes.
Yeah, it seems that the same thing happening here.
Yeah.
We have maybe later.
I think it's exactly what happens here. It's not the same. It's exactly the same, I think.
Maybe it's exactly the same thing, but this connection between that and the statement that you have made, within what I'm going to show, the statement that is made, I haven't completely absorbed it yet, and so it seems that no. Let me see. It seems that I have a counterexample where, well, not really a counterexample, an example where that mechanism doesn't apply, but still we have a quadratic dispersion. Maybe I mentioned that later. Basically, in this context, we will see that this background magnetic field term that I've written here, Ui Uj dot, which according to this argument would be the most important factor that explain the quadratic dispersion relation, is actually not the one that is important here. The one that is important here is that the coupling of the particle to a U1 gauge field. Now I'm writing this coupling here, U dot E. So here what happened is the following. If I have a charged particle displaced by amount U, that causes a dipole moment proportional to U. So this dipole moment is coupled to the electric field. So it's like U dot E. So we will see that actually that one is the one that that explains the quadratic dispersion relation.
I have a comment for that question. So I guess in this case, you have photons and you have discrete transmission. If the discrete transmission and it gives the non-commutativity is proportional to charge. This case charge is also so these two goes above as you said by
It seems that this thing is not one that that's happening here. But let me first tell you why that's so, and then I'm going to. I don't have it on a slide, but I'm going to try to give an example of a possible hypothetical system where there is no Berry phase, there is no this commutator of these two translation they seem to commute, or it's the commutator is expectation value of the commutator is 0, but still the mode has quadratic dispersion. Okay, so let us write down terms in the theory of elasticity of particles. They are moving in a magnetic field, but coupled to a Maxwell field. So here I'm writing all the terms without regard to any coefficients, numerical coefficients. So when you see 1/2 here, it's a symbolic 1/2. It's not real 1/2. Some kind of a coefficient that one have to derive from the theory of Goldstone boson, determined by the equation of state of the Goldstone boson. So we have this term, which is the Maxwell field, coupled through a dipole coupling to the displacement. And for the lattice, we have just the usual lattice action, the action of phonon action, and then we also add this term, this Berry phase term in the Lagrangian. We are now interested in the regime omega of order q squared. That's what we set out. We will see that we get that, but let's assume that in the beginning. So assuming omega of E is order q squared, that means omega is much smaller than q. When omega is much smaller than q, then there are some simplification happen. First of all, this E squared term can be crossed out because E is a dot. So it's a dot square is much smaller than gradient of a square because the time derivative is omega and it's much less than the spatial derivative. So we can cross out E square. Another term that we can cross out is U dot square. Okay, it's small compared to both of the terms that are on the left and on the right. Inside the first term has one derivative and the second term has two but spatial derivatives. So it's better than two time derivatives. So when we have this, now the thing that happened is that one of the equation of motion that we obtained by differentiating the action with respect to A0 becomes an equation with no time derivative. Just say that divergence of U is equal to 0. It comes from this term here, this U dot gradient of A0 coming out from here. So E is gradient A0 minus A dot. Right? So differentiating with respect to A0, we find that the lattice displacement in the low energy limit have to be transverse. The longitudinal mode should be gapped out, should decouple from this low energy regime. So it has to be correspond to something that has dispersion much that is not omega equal q squared. So only transverse mode survive in this our infrared limit, and that allows us to parameterize the lattice displacement by a scalar field, which we call phi. So here we see the first time that there is only one mode instead of two modes of longitudinal and transverse sound. We have now only one. Now we want to understand how this mode, this phi, mixes with the photon and then get us the kachenko mode. So let's do some algebra here. So here U from the last slide, U I is epsilon ij dj phi. Okay. The lattice elastic energy is proportional to derivative of U. In fact, if I write it down, there would be two terms. There's two Young moduli, one shear, the other is bulk. But the bulk one plays no role here because only the transverse sound propagate. And so only the shear modulus G appears. And this term, the elastic energy, becomes just second derivative of phi squared. First derivative of U, of the displacement, but the displacement itself is derivative of the scalar field phi. And so we have gradient of square phi squared. And now another thing that you can see that if you put that into this Berry phase term, you get 0. With 0, just there is no, if there is only one mode, there's no way that one can have a Berry phase. The first time derivative term with one scalar field is always a total derivative. And so we get 0. There's no such thing at this moment. And though everything comes from the interplay, non-trivial interplay, the quadratic dispersion relation comes from the interplay between the terms that we didn't consider before, U A dot. Okay, U A dot.
This question from later.
Is there a question?
Yeah.
Raise hand. Yeah. Nati, can you ask?
Yeah. Before you neglected some terms because you said that they are smaller than the UU dot term.
before, I haven't heard your question.
Earlier, you had a Lagrangian with more terms, and you neglected some of them because you said that they are negligible compared to the UU dot term.
Mhm.
So I'm questioning now whether, now that you realize that the UU dot vanishes, whether you should go back and include the higher derivative terms that you neglected relative.
Maybe I shouldn't say this U dot square term is negligible compared to the G term here in the U dot term. I don't have to use this at all. I can say that this U dot square term is much less than G times gradient of U square term, because omega square much less than Q square. And so I don't have to use the UU dot term.
The reason I'm concerned is more intuitive. The terms with time derivatives tell you which degrees of freedom are dynamical. And by neglecting the U dot square, you went from two modes, from two modes to one, you kind of got a factor of 2 reduction. And now when you set the UU dot term to 0, you're in danger of losing everything. So I guess what you're going to say is that all the terms are not negligible, but they're kind of at higher energy. The
This
other
UU dot term it turned out to contribute to the interaction that we will see. Try to tell
okay, keep
that
going.
later. So it's the fact that it's 0, it appear it's only some kind of a accident of the quadratic approximation.
Well, it's a common thing that whenever you have a single scalar field, there cannot be a one-time derivative term in the Lagrangian. You don't even need to do the algebra. The moment you have only one phi, every term involving phi and time derivative will be a total derivative.
Yeah, but say phi cube term turn out that we can have a cubic term that has single time derivative. I think it will come out from
No,
this.
as long as you write anything which depends only on phi, any function of phi times the time derivative of phi is a total derivative. It depends only on having just one phi. Right, phi to the 7th times phi dot is the total derivative of phi to the 8th.
But I can have phi dot times some combination of derivative of phi.
That you can have, but this will be high order.
That would be higher order, yeah. So
I'm really questioning the argument that you used before when you neglected the U dot square.
I thought
It's very easy to answer this question. Don't neglect it, do the algebra and check whether it affects the answer or not. And I assume it doesn't affect the answer, but the reasoning was incomplete.
Well, the reason doesn't rely on this term at all. We used to have the U dot square term here, but U dot square is smaller compared to this term, to this term. And so I don't have to use the first time derivative term at all to make this argument. I just need to know that the second time derivative term in U can be neglected compared to the second spatial derivative term in the Lagrangian.
Okay, but once you express everything in terms of U, you're going to lose now all the time derivatives. I'm not saying it's wrong. I'm just asking for better clarification. So if you tell me that in the end of the day, you find the Lagrangian at the bottom of the slide, I have no problem with that. My problem is only with the logic that leads to it.
Yeah, I at the end of the day, the calculation gives rise to what show that this UU dot term can be neglected. But I don't understand why the argument that I just gave doesn't work. That is, when I have U dot square term and I'm looking at omega much less than q square, omega square much less than q square regime, that term clearly is smaller than the spatial derivative term. So, so this u dot term squared is neglected, and after that, everything just follow.
Okay, keep going.
Yeah, maybe there's something I don't understand, but I can also do the calculation with the Berry phase term included, and its effect it doesn't affect the effective Lagrangian. We can what people did is to include both u dot term and u dot square term. So here, so this Lagrangian is easy to solve with all the term without neglecting anything, and that one can verify that what the term that are dropped here can actually be dropped without changing the speed of the phi, the dispersion relation of the phi particles.
But the question, when you say that phi is the superfluid phase, that looks compact, but then when you say it comes from free velocity, it's not clear.
I haven't said that this phi is superfluid phase yet, but the choice of the notation suggests that it's a superfluid phase, and that's what I'm going to show you now.
That's what I'm asking. I guess I made a couple of statements. I didn't ask you a question. The question is phi compact?
I think it should be compact.
Can you?
Yeah, I can. Yeah, why? Well, the question was whether phi is a compact scalar field like a superfluid phase. I think it should be. Yeah, as I going to show here. So we have a term u a dot minus a half of b squared. So u a dot is, we know that this u is equal to epsilon ij dj of phi, and here I have a I dot. I can do integration by part and pushing the time derivative and spatial derivative in different direction, and then I get phi dot minus b. So these two terms, phi naught minus phi naught times b minus b squared, then can be integrated over b. Although this b seems to be a field that comes from inside curve of A, but all configuration of b's are allowed, and so we can integrate over b and get a phi dot square.
Maybe this term makes Nadi happy because you're saying there secretly is a u dot term that survives that you integrate this by parts. You have a single time derivative of u term sitting right there.
If you have u dots,
After you integrate it by part, that is a u dot term. I think Nadi was complaining you had no more time derivatives on u whatsoever, but you have one term.
oh, maybe I didn't understand what Nati was concerned about. So this gives the time derivative term to the dynamics of phi. Comes really from, now you see that it's this phi dot square come really from the coupling of the phonons with the photon. So the mixing, basically a mixing of phonon with photon. So we have this phi dot square, and you see here.
Again, what bothers me here. Before, I'm not disputing the last answer. That's not my problem. My problem was in the derivation. You neglected the term with u dot square, which could have given double derivative.
Which could give a term that has more derivatives than the ones that
More spatial derivatives, but not more time derivative.
More spatial derivatives.
Okay, now I understand. Okay, thank you.
Yeah, it has also two time derivatives. So this step looks like we are doing we are doing duality in reverse, right? Reverse is, if you remember how duality is usually done, we just introduce some kind of auxiliary field that enforces the Bianchi identity and then integrate out the field that get it. This looks like we are doing that in reverse. So I think this phi must be a superfluid phase. So somehow in this Kachenko mode, we have a locking between the superfluid phase fluctuation and the lattice fluctuation. Lattice fluctuation is a derivative of that superfluid phase. And the final Lagrangian of the Kachenko mode then becomes the phi dot square minus the elastic energy, that is gradient square of phi square. And so from that, we see that it's omega equal q square. Okay, so now this is an example of, I think, of the fact here is that we, in this derivation, we did not rely on the Berry phase term, this term here in any capacity. This one seems to play no role in setting up the quadratic dispersion relation. One can ask whether one can have a physical situation in which we have a lattice, but lattice of things that have lattice. Imagine you have a lattice of charged particles. Maybe I draw a picture. New page. So imagine that we have a situation where we have in 2 dimensions a lattice of charged particles embedded in a gallium of negatively charged background, and all that coupled just to a U1 gauge field without any magnetic field at all. There's no background magnetic field.
So this U1 gauge field is in 2D.
2D. Suppose I have a 2D system. We can talk about 3D later. But the 2D system would be enough. A 2D system coupled to a U1, 2D U1 gauge field with no magnetic field at all. And then this system, repeating the calculation that we have done here, we see that this perfectly quadratic dispersion relation. There's which cannot be explained, doesn't seem to be related to the non-commutativity of the 2 translations at all. Now, where that system can appear. So imagine the following. I have more like a sci-fi proposal. Let's imagine we have a half-field Landau level. Mention a half-field Landau level, which is, as we know, is a liquid, Fermi liquid of composite fermion. But imagine that we somehow manage to make it crystallize. It becomes a crystal of something, a crystal of things that carries the charge of the composite fermion. If the system is completely particle-hole symmetric, then this map almost completely into this situation. Okay.
This field is relevant to Wigner crystal.
Wigner crystal. Wigner crystal seems to be completely a different situation. That's something I'm also not completely sure. So Wigner crystal is a crystal of particles in a magnetic field. And the quadratic dispersion seems to be related to the fact that you have this Berry phase. So not sure what is the, on the first side, it seems to be 2 different mechanisms to give a quadratic dispersion.
There's also Coulomb interaction.
Yeah, but in the Wigner crystal, you don't need to have a magnetic interaction between the particles. So here, what is important is that the interaction is not only a Coulomb, but there is also magnetic, that UA dot, right, minus p square. It's a magnetic interaction.
Can I come back to this question of whether phi is compactor? Is that all It's not as important for response, but it's important for other things with this theory. Certainly the superfluid phase that you would start with is compact. But this phi, in its definition, you're passing from the velocity to phi. And in doing so, phi and phi plus any constant give the same velocity profile. So wouldn't that mean that when you pass from the path integral over u to the path integral over phi, that you identify, you introduce a new redundancy in your description, phi and phi plus constant give the same u, in which case you would identify the two and say phi doesn't have, it's not compact, well, it's compact, but it has 0 radius. Say you identify phi and phi plus any constant.
Definitely the 0 mode is not there.
Exactly. You delete the 0 mode, I think, when you pass from phi.
Difficult question. Something that, yeah, I hope that is. But now I have a motivation to think more deeply about this, to think more about this nature of phi. But it's.
So there was a talk on Tuesday by Pranay Garantala studying the plot Lagrangian while keeping the 0.
Mm-hmm.
And there are all kinds of infinite degeneracy.
Yeah.
Not sure about your model.
Without the 0 mode, this is a very nice theory, and with the 0 mode, it's a very strange theory.
The one thing I'm going to ask is whether one can have a vortex of phi. That vortex of phi is very simple to understand in the term of the lattice. It's the vortex of phi correspond to a vacancy in the lattice. Natural dimension for phi. So the phi here, since I've written everything in this language, actually, if we do the calculation more accurately, the natural thing to write here is to write an L square, so that phi has a dimension 0, phi dimensionless. And this L, basically, this is the magnetic length. Because when you rotate, it corresponds to a magnetic field, and this L square is proportional to 1 divided by the magnetic field. Okay, so linear is the theory. Okay, so now this theory seems to have a symmetry that enhanced compared to the usual symmetry of the superfluid, at least to the quadratic level, because the relationship between the displacement and phi involve the first derivative, and so spatial translation of the lattice correspond to translating phi, adding it to phi term that is linear in space. Now I can ask, what is the decay of the Kachenko mode? Can a Kachenko mode decay, and what is the rate of that decay? So the first question can be answered by just looking at the kinematics of the process of one particle going into two. And we know that if the dispersion relation curve upward, then this decay is possible. And it is going upward because omega is equal to q squared. And so such a decay should be, if it's not forbidden by any symmetry, then it must happen. And the next question is, what is the term that involves phi cube that has the smallest number of derivatives? So that will determine the rate of decay. So let me give a naive argument. At the end, I think it gives the correct result, but I think the answer, the more accurate derivation of the answer is more subtle than what I'm going to say here. The naive argument is the following: is that under this exotic symmetry that we have, phi goes to phi plus a constant plus a function of x, means that when you write down a Lagrangian terms that contains phi by itself, or phi with only one spatial derivative acting on it, should be forbidden. So things that we can write down have to have sufficient number of derivatives, spatial and time derivative, to kill off this c and a times a dot x that we could add to phi.
Scale x, same as translate
We can translate the whole lattice by a finite amount.
yeah.
That corresponds to phi go to phi plus a times x.
I see.
And that's because u, remember, u is derivative of phi. So that's.
But then if you translate by one lattice sign, by one lattice spacing, then
But that is not the, that doesn't seem to be the periodicity of phi. It's like adding, yeah, sorry. It's like adding the periodicity of the lattice. First of all, this is a very, it's a microscopic, it seems to be a microscopic, we need knowledge whether this lattice is square or the lattice is cubic or hexagonal or something. And then it means that the lattice comes to itself under phi plus 5 times certain a vector times x. That I'm not completely sure I understand that. It's not a periodicity of phi. So I think different kind of identification.
yeah, but you want to identify. But maybe I say it's
Maybe, yeah, maybe we need to identify.
Can you please put the original Lagrangian with U?
I'm sorry?
Before- Can you please put back the original Lagrangian with U?
Yeah.
Okay, so this Lagrangian has a symmetry shifting U by a constant, except perhaps the term with U times E.
Except term u times e,
You can shift U by a constant.
I can shift u by
That is what translates under your change of variables to a shift of phi by a linear term.
So this shift L by E, which is only a total derivative.
Okay, ignoring various global considerations.
Mhm.
And why don't you include at this stage other terms like U square, for instance?
So u square cannot appear in the Lagrangian because again this lattice here, if we shift the lattice by a constant, nothing should happen. The say the energy, the static, the elastic energy should not change if we just shift all the point of the lattice by the same amount.
So you're saying that your starting point is a Lagrangian with a shift symmetry for U?
Yes.
And that shift symmetry, is it compact or non-compact, or what should we do about it before we start changing variables?
You mean the lattice, the whether
Okay. This is your starting point, this Lagrangian. I didn't understand the lattice and all that. You have this Lagrangian.
Mhm.
And then you change variables to U, to phi, and then you went to low energies, and then you found the Lagrangian for phi. So I'm trying to understand the fields here. Is U compact or not?
Is U compact or not?
Yeah.
So U here, I think U must be at least U must be compactified on a torus, I think, because
U should be, so U takes values on the torus.
U should I think you should take value on the torus.
Good. So if you try to shift u by a constant, that constant is also periodic.
If I shift phi by a constant, u by a constant, then what do you say about this constant?
If the periodicity of y, if y takes values on the torus, sorry, if u takes values on the torus,
Yeah.
then u goes to u plus a constant. That constant is also on a torus.
Yeah. So u plus a constant, and that constant basically on a torus. Yeah.
Good. So now that translates, this A is what you called A in the transformation for phi.
This A is also,
Transformation phi goes to phi plus AX. It's
yeah,
the same A.
this u goes to basically the same A, maybe with the different kind of index. So u goes to
I don't care about the index. So,
Yeah,
so
epsilon I.
A here is periodic.
So here, yeah, it's periodic.
Right. Is this important or not? So there are really two questions here that people ask.
Yeah.
One is the zero mode of phi, whether it's compact or not. And the second is whether A is compact or not.
It looks to be, should be at the end important, but I don't know where.
And space itself, is it compact or not?
Space itself, we can do whatever with it.
Okay, so let's make X compact.
Yeah, we can make X compact.
In order to have this transformation, phi should better be compact. And we have already agreed that A is compact.
Mhm.
So there's a very small finite set of A's that are allowed.
There is a continuous A is allowed to be in some continuous, it's a continuous function, but
Yeah, but then it will not be
periodicity.
consistent with the periodicity of phi.
Yeah,
So if phi is non-compact, then A should vanish. And if phi is compact, A could take a small set of values. I think there are at least possibly many more people in the audience who know more than I do about this issue.
that doesn't include me. Unfortunately. But I think it is an interesting question which can be an answer because everything here has a physical, the map between u and phi. One thing that might be, we have to be careful is the solving these equations.
May I ask a clarifying question? So when you say u takes value on torus, is it because u is the displacement, and if you move by lattice constant, doesn't change the value?
Yeah, yeah. We should get to the. So when I think maybe one of the places that one should be more careful is in this solving this equation. I assume that when divergence of u equal to 0, u at infinity is 0, and so right, u is equal epsilon I j d I phi. But suppose I have u on a torus. Divergence of u can be 0, but then solving that would require, would be more non-trivial. But it's an interesting question, I think.
just a comment. One benefit of going through this discussion is then clear that this this phi goes to pi plus vector out into x. This should be a symmetry of your effective theory of phi because as you uniformly displace your lattice, it's the same thing. That's a symmetry.
Yeah.
Otherwise, it's not clear why you should enforce these symmetries on your higher derivative directions.
I think there is this question, and there is also another question that I think maybe I can mention at the last minute, 5 minutes or so. Okay, so if we follow this argument, then the term that we can write in the that contains phi cube, 3 power of phi. One of the term would be grad square phi cube, and from this term we can deduce that the rate of decay of one particle into two decreases like E cube on the limit when the energy of this magnetoroton goes to zero. So the Kachenko mode goes to zero. That means that the Kachenko mode becomes more and more well-defined particle as we go to in the infrared. Similar behavior observed for any other Goldstone bosons, where Goldstone boson of superfluid also becomes more and more well-defined when we go to the infrared. Now, this result I couldn't find in the literature. Now, in the literature, there are I found only one article where people consider the decay of the Kachenko mode, and the claim in this article is that the rate of decay actually scale like E. The rate scale like E is something I don't think I can accept. And so I think that there must be something wrong with this calculation, which I haven't been able to find.
There's no phi minus phi symmetry.
There's no phi goes to minus phi symmetry.
U goes to minus U.
U goes to minus U. Let me go back to here. I think there is none. This the symmetry isn't. So the question is whether there is a phi goes to minus phi symmetry. U go to minus U is not a symmetry. It turned out that it flipped the sign of this U dot E term.
And you also flip the sign of the gauge.
Also put the sign on gauge E. Doing some spatial inversion.
You can flip the sign of E.
There is AC2 symmetry. So gauge field. No, but in particular, it integrates out.
Let me see. There is also all the other kind of terms that would survive. Let me see. I used to have. I think I used to have a good argument why phi. We don't have phi goes to minus phi symmetry. It isn't any symmetry that that microscopic theory would have. The microscopic problem has only doesn't have this kind of Z2 symmetry. So it would appear, yeah, it would always appear at some point. Yeah, I'll show you where it appears. Okay, so now maybe I have until 10:40. So this.
Cubic term. Should we worry about the underlying triangular length? Additional inheritance or
Yeah. So this cubic term, if it's cubic, then there is one term that's allowed, that is dx plus basically is this one, phi square and then cube. Plus Hermitian conjugate. This breaks rotational symmetry but preserves the rotation by 60 degrees. Okay, so maybe it's very quickly what we are trying to do next is to try to understand a nonlinear treatment of the problem. So we want to include in the theory nonlinear effects like the nonlinear elasticity effect. And here the nice formalism is to think about the lattice as a map between external spatial coordinates and the frozen coordinates, frozen in the solid. So each of a point would be associated with a point in space, but also a point in space where that point would be if the solid wasn't deformed. So it's a relationship between x, small x, and capital X, and this capital X is basically small x minus the displacement. So in this picture, the vortex number current, each of these points is a vortex, so the vortex unnumbered current becomes a current that is conserved. And then let me identify the problem first, that the constraint in this nonlinear regime becomes much more non-trivial. In the linear regime, we could have said that the displacement has to be divergence free. But here we have a nonlinear equation. This nonlinear equation just say that the map from x to small x to capital X is an area preserving diffeomorphism. So the problem is how to write down a field theory where the fundamental degrees of freedom is elements of the area preserving diffeomorphism group. So let me just very quickly what we do. We say that the volume area preserving diff can be thought of as canonical transformation. So think about x1 and x2 as the two non-commuting canonical x and p. And then area preserving diff basically is the canonical transformation in this space. And that is the way that we can devise a parameterization of all area preserving diff. We know that infinitesimal canonical transformation is generated by the functions phi like this. We take a Poisson bracket of phi with x. So this formula reproduces what we have before, but we can go to higher order. The exponentiation of the infinitesimal volume preserving diff give us the way to make this to basically parameterize this nonlinearly. So this is what I won't have time to talk about. And the upshot is that the decay rate, we get all kind of nonlinear term. The decay of the kachenko mode still have the cubic dependence on the energy. Okay, thank you.
Okay. Any questions from the audience?
We have a question on Zoom.
Should I go first? Or okay. For the Lagrangian of U, what's the region of validity of that Lagrangian to describe the underlying microscopic lattice? For example, does U have to be small?
U has small derivative.
The U itself.
Yeah. The more nonlinear version of this make it very clear. X can be X. This X have to be smooth function of small x, but they don't have to be anything related to small x.
We have a question from Zoom. I think John has a question.
Yeah, hi. I was wondering what is the effect on the story of weakly gauging the symmetry that's spontaneously broken, like in the Abrikosov lattice of a real superconductor?
Weakly gauging the phi, I think the effect may be dramatic because basically here you want to add a, roughly speaking, is this what you would like to have? This is some a square term?
No, I don't think so. No, that would be Higgsing this one, right? No, I just mean like is there a similar kachenko, I don't know how to pronounce it, kachenko mode in the Abrikosov lattice of a superconductor, like a thin film superconductor?
From what I understand, then this mixing of the Goldstone boson with the lattice doesn't occur. So you have lattice fluctuations, but there's nothing that it can hybridize to with. There's nothing it can mix it with. And so I would assume that the dispersion relation becomes linear at in the infrared when you are below the gap of the that you want to gap out the photon, right? Yeah, I still think you don't, or is it not what do you mean by?
Well, yeah, I guess I'm
superconductor. There is no Goldstone boson because it is eaten away, so it becomes a gap mode.
So in that case, you just get a linear dispersion.
I think so. Yeah.
Okay, thanks.
Just a quick question. What's in your nonlinear completion at the end? What's the fate of this funny linear A dot X symmetry that you had in the linearized theory?
It becomes a nonlinear symmetry. So the formula that we have written here turn out to be a bit too simplistic. The A turn out that this becomes A phi. So roughly speaking, this e to the phi is volume preserving diff, and you can multiply a translation or rotation on the left, like a translation that looks like e to the power of alpha dot x. Well, multiplication implies some Poisson brackets, and so when you multiply this, this becomes e to the power of phi plus alpha x, but you also get this from Baker-Hausdorff phi alpha x type of term and all other terms, so it becomes nonlinear.
Do you have any questions on Zoom? Okay, any question from the audience?
So before in the effective field theory, you add this like cubic terms, and if you trace back to the original theories using U, what is the things that you need to add to induce that?
So various things. First of all, even the term that is already here, they secretly already have interaction because the translation from U to phi becomes nonlinear. There's nonlinear correction, and also there could be cubic term in the elastic energy. The elastic energy can also have a cubic term.
Any questions from the audience or from Zoom? Okay, let's finish then and have a coffee break.